All right. So we're going to start with testing for serial correlation. I'm going to go back and forth from the slide deck to Stata, as always, to provide you with kind of like more nuance on, the empirical side of the discussion. But I'm going to start first with some motivating example. So in the previous week, we discussed about the Phillips curve, and then in particular, we discussed about the expectations augmented Phillips curve. If you remember from the lecture last week, if we just regress inflation on unemployment in a contemporaneous manner, then we would obtain a positive relationship between inflation and unemployment, which is quite different with what the theory posits. The theory suggests that there is a negative relationship with inflation and unemployment, but if we just regress the two variables in a contemporaneous manner, we would obtain actually a positive relationship. And so one of the things that causes the issue, the theory says it's negative, but in empirics we say it's positive. It could be due to misspecification. So that's something that we need to address. And in this particular case, we're going to augment the Phillips curve in such a way that it would include an expectation term. So if you look at here, the inflation is going to be adjusted by some expected inflation. Okay, so the difference between the actual and the expected inflation is called the unanticipated inflation. And then the difference between the actual unemployment and then the natural rate of unemployment is going to be called the cyclical unemployment. So rather than regressing inflation on unemployment, what we do is we adjust the inflation with the expected rate of inflation. In this particular case, we can use the previous period inflation. We call this the adaptive expectation. And then we regress it on unemployment. Now, this is kind of like, one of the things that we need to consider when we're doing time series econometrics. So specification is very, very important for us to get the, the robust result. So, this is the same slide, so I can skip this. So in practice, we're going to use the previous period inflation as the expected inflation. In this particular case, we're going to name this as adaptive expectation. Okay, so we have adaptive expectations in which we use the inflation at t-1. Okay, so there are recent theories that suggest inflation expectation is not only based on previous period inflation or adaptive expectation, but inflation expectation could also be due to forward-looking expectation. So what you think is going to happen in the next period. And so I think that's one of the more interesting thing, but for today's lecture, we're just going to focus on adaptive expectation. And so if we regress the difference in inflation and the adaptive expectation, and we regress it to unemployment, then we may obtain a better estimate than when we just regress inflation on unemployment. Okay. Now, anyone recall what are the assumptions that you need so that you're going to obtain a consistent estimate of beta 1? So if you can name two assumptions that are key to the estimation of beta 1, please raise your hand. Anyone?
Can I, sir?
Yeah, go ahead, Zaki.
So the assumptions that we have to fulfill to obtain a consistent estimate using OLS is the time series assumption 1 through 3. which are the linearity and weak dependence. Then we also have to assume for the no perfect collinearity, and we also have to satisfy the zero conditional mean assumption, which requires a condition that is also referred to as the strict exogeneity.
Okay, very good, Sakti. Thank you so much. So I guess the first and the most important thing to get a consistent estimate of beta 1 is going to be stationarity. So you need to have stationary unemployment, and you need to have stationary unanticipated inflation. And then the second assumption, of course, there is no perfect multicollinearity, but what's more important is there is strict exogeneity. So there is no correlation between between unemployment and the shocks contemporaneously. Okay, contemporaneously means at the same period. There is no correlation between the shocks and the unemployment. So that's going to be the main assumptions that we need for us to obtain a consistent estimate of beta 1. Okay. So I'm going to go to Stata just to provide you with an illustration of the estimation and how the estimation could basically fail if there is issues with the regression. So I've uploaded here the Phillips curve data, and then I'm going to do the TS set, as usual. Well, here is going to be the time series indicator for the data set. And first, I'm going to show you the static Phillips curve regression. So if you regress inflation on unemployment for the beginning of the data set until 1996, okay? Now, the first thing that you'll notice is that the estimated coefficient is positive, which is quite different with the theory posits, okay? So this is an indication that maybe there is an issue with the regression specification, okay? And so you need to check with the regression specification to make sure that you don't leave out any important assumption, for example. After you check the specification and then redo the analysis with, say, a better specification, and then you still get a positive results, then perhaps a positive relationship is indeed the feature of the data. However, if you think that there is an issue with the specification, and then you redo the specification and redo the analysis, and once you redo the analysis, you actually obtain a different results than your initial estimate, is actually an estimate with a biased result, okay? So in this particular case, I'm going to do a regression on the difference in inflation. So basically, this is inflation minus inflation T minus 1. And then unemployment, if year is below or equal to 1996, okay? Now, as you can see, after you did a minor tweak on the specification to include expectation of inflation, the estimated coefficient is now negative 0.542, which is quite in line with what the theory says. Furthermore, it's also statistically significant, okay, which is quite different with the previous estimate. So what does it say? It says that, one, understanding about specification of the model is very important. So how do you make sure that the specification that you use for the estimation is more or less correct? The first thing that you can do is actually stay true to the theory. Okay, you always have to go back to the theory, and then what does the theory say? Yes, a very classic theory back in the 1940s, 1950s is going to tell you that a regression between inflation and unemployment is sufficient. However, with the recent development of theories, then it's not enough just to regress inflation and unemployment, because in practice, people have expectations on inflation, and then the expectation of inflation is going to allow them to make decisions that would affect the relationship between inflation and unemployment. So starting with the theory, I think that's very, very important. And then from there, you can adjust the regression specification to ensure that it's in line with the theory. Okay, so any questions on the regression itself before I go and discuss a couple of things? Go ahead. Okay, very well. If there is no question at this moment, I'm going to continue. So I'm going to go back to the initial regression. Okay, so this is a regression, a static regression on inflation and unemployment. After I do the regression, what I'm going to do is I'm going to calculate the residual. Okay, and then I'm going to use the Correlogram analysis to look at the structure of the residual. Okay, so if you remember from the Correlogram analysis, what you can do is you can understand the autocorrelation as well as the partial autocorrelation of the data. And as you can see right here in this particular model, the residual has a relatively high autocorrelation. In particular, there is a high autocorrelation in the first lag. Okay, and so if you remember, one of the assumptions that we need to obtain efficient estimate of the regression parameter is to ensure that there is no serial correlation in the unobservable, okay, or the error terms. However, this particular correlogram shows that there is indeed a serial correlation present, okay, and this could affect our estimate, okay. Again, it's an estimate of the standard error, not the estimate of the parameter. Now, I'm going to contrast this with the regression of inflation and adaptive expectation and unemployment. Okay, so I'm going to do the same, and then I'm going to predict the residual. Okay, and I'm going to do a Correlogram analysis on the residual. Now, as you can see in leg 1, there is basically almost no autocorrelation, which is relatively close to 0. Okay. However, there is a relatively large spike in period 2. So that could indicate that there could be a serial correlation at leg 2. However, given the estimated autocorrelation coefficient of 0.39, perhaps the autocorrelation is not that big. Okay, so what are the takeaway from this particular exercise? First one, we need to get the regression specification correct. And one of the ways to make sure that we get the regression specification correct is to make sure that we stay in line with the theory, particularly the more recent theory. Second, we need to make sure that there is no serial correlation, because if there is a serial correlation, then our regression estimate is not going to be as efficient. And so what we're going to discuss today is to dig deep into the no serial correlation assumption. What would happen if we violate the no serial correlation assumption? And what are the remedials if we have a serial correlation issue? So that's going to be our discussion today. Okay. Now I'm going to go back to the slides, and then we're gonna again discuss several issues regarding the no serial correlation assumption. Now, before that, I'm going to open up the floor if you have any questions or clarification regarding the explanation that we just had. Go ahead. All right. Okay. So as you can see from the Correlogram analysis of the residual, you'll see that the errors of the time series data are autocorrelated. Okay. So again, in this lecture, we're going to learn the consequences of serial correlation, how to detect the autocorrelation, and then a remedial to actually address the issue of autocorrelation. Now, we're going to go back just to go through the assumptions. So if you recall, there is the stationarity assumption, linearity assumption of the parameters. We also have the no perfect multicollinearity assumption, variation in the explanatory variables, as well as the strict exogeneity assumption, or the zero conditional mean in contemporaneous setting. So if we fulfill the first, second, and third as assumptions, then we're going to obtain consistent estimate of the parameters. Okay. Now, again, in this particular theorem, there is there's no mention of serial correlation. Okay. Why? If you remember, the issue of heteroscedasticity, the issue of serial correlation is not going to affect whether or not we get a consistent estimate. Okay. Now, just a very brief note. In the earlier stage of this course, we learned about cross-section data, we learned about full cross-section data, and then we always mention that if we fulfill OLS assumption 1, 2, 3, and 4, we're going to get an unbiased estimate. Okay, so basically consistent estimate and an unbiased estimate are relatively, it's not the same concept, but it's a similar concept. The property that you want to achieve for an estimate is either you have an unbiased estimate, or for some particular setting, you want a consistent estimate. So that's the ideal goal of an estimation. Okay. All right. Now, I'm going to go through the next assumption. So this particular assumption suggests that conditional on the relationship between the unobservable variable across time, then there should be no correlation between the error term in period T and error term in period S. Okay, so in other words, this particular assumption says that the error terms shouldn't be correlated. Okay, we can also say that there is no serial correlation, or there is no autocorrelation between the error terms. So this is what the assumption says. Okay. However, in many time series econometric setting, we are very likely to violate this particular assumption. Okay. So the current shock or the current error term is going to be correlated with the past error terms. Okay. If that's the case, then we're going to deal with the issue of serial correlation or the autocorrelation issue. So this is something that we couldn't eliminate by manipulating the data. This is actually a feature of the data, and this is a very common feature of time series econometrics data. So if you have an issue of autocorrelation, or if you have an issue of serial correlation, you don't have to panic. What you need to do is try to understand what's the consequences of violating the no autocorrelation or the no serial correlation assumption, and then what you can do to remedy the situation. Okay, because that's the feature of the data. It's the same principle when you have heteroscedasticity in your data. it's a feature of the data. So you wouldn't be able to kind of like manipulate the data in such a way that, you know, the heteroscedasticity is going to go away. But given heteroscedasticity, how can you make a better inference out of it? So one of the things that you can do is to have the heteroscedasticity robust standard error. All right, so that's going to be on the serial correlation. So if you violate the no serial correlation assumption, or if you violate the no autocorrelation assumption, then the estimate of the beta hat J is still going to be consistent. That is, if you fulfill the assumption TS1, TS2, TS3. However, in addition to estimating beta hat J, we're also interested in estimating the standard error of the beta hat J. Now, if you violate the no serial correlation assumption, then your standard error of beta hat J is going to be invalid. Okay, and if you remember, the t-test for you to do hypothesis testing is going to be a ratio between beta hat J minus beta J and then standard error of beta hat J. Right? So if the denominator is invalid, then the t statistics is going to be invalid. Okay. So basically, if you have serial correlation, although your beta hat J is going to be consistent, but your t-test, your f-test, your chi-square test is going to be invalid. Why? Because your denominator, in this particular case, is the standard error of beta hat J, is going to be invalid. Okay, so that's the main consequences. Now, the question is, all right, we still get a consistent estimate of the beta hat J, then why do we care at all about the t-test? If you recall, the t-test is very important for us to obtain the correct inference. We want to avoid any issue with type 1 error, where we reject the true null hypothesis, or we want to avoid a situation like the type 2 error, where we fail to reject the false null hypothesis. Okay, and so having a valid standard error is going to allow us to make a better inference. If there is no effect, then there's truly no effect. But if there is a significant effect, then we want the estimate to actually allow us to detect that significant effect. All right. Any questions from the floor regarding this particular matter? Right? Cool. Then I'll continue. Okay. So we've seen the autocorrelation graph, and this is something that we also see that we also saw in the previous lecture. And so basically, a correlogram analysis is going to provide you with the autocorrelation as well as the partial autocorrelation. Okay. So in particular, we focus on the residuals of the model, and then given the residuals of the model, we want to see whether the residual at a particular time t is correlated with the previous periods. It could be t-1, it could be t-2 until t-j. Okay, so the most ideal situation is that there is no serial correlation. It means that in the sample analog, we don't see any relationship between the residual today and the residual in the previous period. So that's the most important thing. Okay. So when we do your analysis, it's always nice for you to look at the residuals, and then given the residuals, look at the correlogram analysis. Okay. Now, in addition to having information about the autocorrelation, the correlogram analysis is going to provide you with the partial autocorrelation function. Okay, so the question is, what's the difference between autocorrelation and partial autocorrelation function? Okay, so suppose that we have two periods in the data that is relatively some periods apart. So we have t and then t minus 1, t minus 2, and then t minus 3. Okay, and so the correlation between residual at time t and then at t minus 3 is going to be autocorrelation. Okay, so that's going to be the autocorrelation between t and then t minus 3. So what about the partial autocorrelation? So the partial autocorrelation is still the correlation between the observation that we observed today and then the observation at t minus 3, controlling for relationship until t minus 2. Okay, so again, partial autocorrelation between t and t minus 3 is the correlation between that, controlling for the relationship between t and then t minus 2. So that's the difference between autocorrelation and then partial autocorrelation. If you're interested in advanced time series analysis, so for example, if you're interested in doing forecasting, then understanding the structure of the autocorrelation as well as the partial autocorrelation is going to allow us to identify a proper model, for estimation and then eventually for forecasting, right? But for now, what's important for us is to understand whether or not the observation at period t is correlated with the observation at period t minus j. Okay, and if there is that correlation, then we're going to get the consequences that we discussed in the previous slides. Okay, so if you're interested in looking at what's going to be the ideal lag for our analysis, then we can resort to what's called the information criterion. So Stata allow us to actually obtain some information criterion after we do some regression. So there is Akaike information criterion or the AIC. There is the Schwarz-Bayesian information criterion, SPIC, as well as Hannan-Quinn information criterion. And so if during analysis of time series data, we need an information about what's the proper length, so how many lag should I include in the model, then one of the things that we can do is to try to resort to this particular lags. However, in practice, if you start to use more than one indicator, then you could actually get conflicting indicators. So indicator A says that, oh, the optimal lag is 2 lags, and then the other says that, oh, the optimal lag is just is actually just 1 lag. If you have that conflicting indicators, then Ivanov and Kilian at 2001 recommends this particular classification. If you have a monthly data, then information on the Akaike information criterion is more relevant. If you have quarterly data with large sample, you can use the HQIC or the Schwarz-Bayesian information criterion. And if you have quarterly data with any sample size, you can use the Schwarz-Bayesian information criterion. Okay, so these are kind of like good practical information that you need, in particular if you need to select the lag length. All right, I'm going to open the floor for questions and clarification before I go and discuss the definition of the AR1 autocorrelation. Go ahead. Okay. All right, I'll continue. And again, feel free. Anytime you have clarifications or questions, please, address it right away so that, you go into the next concept with a full understanding of the previous concepts. Okay. All right. So let's go into the discussion of AR1 serial correlation. So we're interested in a simple linear model. Again, we can always extend it to a model with more explanatory variables. So for example, you regress YT on X1T, X23, X33, and so on. Okay, but for simplicity of the discussion today, we're just gonna assume a very simple linear model. So you have a very simple linear model, and then you have these error terms. And then the error terms follows an autocorrelation of degree 1 process. So autocorrelation of degree 1 process is the following. So UT is a function of rho UT minus 1 plus some white noise error. Okay, this is called the white noise error. So the white noise error has a very very attractive properties. So the white noise error is normally distributed with mean of 0 and then variance of sigma squared. So this is just pure random error. Okay. Now, what we're interested here is actually the autocorrelation coefficient. And the autocorrelation coefficient is depicted by this symbol rho. Okay, so this is rho, okay, and this is going to be the autocorrelation coefficient. So in this very particular example, I just assume that it's an autocorrelation of degree 1. In practice, it could be autocorrelation of degree 2, for example. Okay, but again, for simplicity and for the sake of introduction, I'm just going to focus on autocorrelation of degree 1. Okay. Now, another assumption that we're going to make is that in absolute term, the autocorrelation is going to be less than 1. Okay, so it could be negative, it could be positive. However, in absolute term, it has to be lower than 1. Okay. So that's a mathematical assumption. So if you're interested in looking at why we need the absolute value of the autocorrelation coefficient be lower than 1, then you can revisit your mathematics for economics lecture. Okay. In particular, you can look at the difference equation. All right. Okay, so again, we discussed about the white noise error. So the white noise error has a very appealing assumption. It's normally distributed with mean of 0 and variance, which is a constant. Okay, and we also assume that there is no serial correlation between the white noise error at period t and then white noise error at period s. So what does it tell you? So what it tells you is that we can now just focus on the structure of the autocorrelation of the error terms. Okay, so we don't have to worry about the white noise error. So the assumption that we impose on the white noise error is going to allow us to focus on the more pressing issue. In this particular case, is the autocorrelation itself. And so let's go and discuss the consequence of having serial correlation in the data. Okay, and again, the serial correlation of the data is going to be depicted by this autocorrelation rho. Now, if you recall from your chapter 2 discussion, you can observe that the variance of an estimate is just going to be the ratio between the variance of the error terms and then the variance of the explanatory variable x. However, the formula for the variance assume that there is no autocorrelation. Okay, so what would happen if there is a serial correlation in the data? Okay, what would happen if there is autocorrelation in the data? In particular, what would happen if rho is non-zero? It could be positive, it could be negative, as well. Well, the answer is the following. So this is going to be the bias if there is serial correlation in the data. Okay. Now, the issue is that we never know whether the bias is biased downward or is it biased upward. Why is that the case? Well, it's going to really depend on the value of rho to the power of j, and it's also going to depend on the multiplication, the product between xt and then xt minus j for all t as well as for all j. So, upfront, we could never tell whether we're going to have an upward bias or we're going to have a downward bias. So it's going to be affected by those different products. Okay. Now we're going to dig deep into the bias of the OLS variance. Okay. In particular, we want to try to understand whether or not there's going to be a positive bias or whether there's going to be a negative bias. Okay. Let's focus on this particular equation. Okay. So let me go back just a couple of slides. Why do we care about this particular portion of the estimate? Because this particular portion is already positive. Okay. Since this particular portion of the formula is already positive, then what we want to know is we want to know whether this portion is positive or is it actually negative. Okay. And so whether the bias is positive or negative is going to be dependent on the interaction between the autocorrelation coefficient as well as the product between xt and xt minus j. All right. So first, suppose that the autocorrelation coefficient is positive. Okay, so either it's to the power of, so for all j, then the autocorrelation to the power of j is always going to be positive. And if we also assume that the xt and then the xt minus j is positive, then the bias is positive. Okay, so in this case, the bias is positive. So what does it mean? It means that the estimate of the standard error given the OLS is lower than the actual standard error. Okay, sorry. So in this particular case, the bias is going to be downward actually. So let me revise. In this particular case, the bias is actually going to be downward. Why? Because the estimate that we get from the OLS is actually lower than the actual standard error, accounting for the serial correlation. All right. Now, since the bias is positive, again, as I mentioned and revised in the previous statement, we're going to have a bias downward standard error. Okay. So in other words, the OLS estimate of the standard error is going to understate the true variance. So if you recall the t statistics, and the t statistics is the ratio between the beta hat j and the standard error of the beta hat j. Okay, Now, if the standard error is biased downward, then the t statistic is going to be biased upward. Okay, so if the t statistics is biased upward, then the probability of type 1 error is higher. Okay, so this is going to increase the probability of type 1 error. All right. So the next case is suppose that, so earlier we assumed that rho is positive, but it could also be the case that rho is negative. Okay, so if rho is negative, then recall that if you have rho to the power of 1, it's going to be negative. If you have rho to the power of 2, it's going to be positive. If you have rho to the power of 3, it's going to be negative, and so on. Okay, so if rho is negative, it's very, very difficult for us to determine whether the bias is going to be positive or the bias is going to be negative. Okay, so again, in this particular case, it's really hard for us to pin down. Now, suppose that, if we want to make some assumption that the bias is negative. So the bias here is negative. And so in this particular case, the OLS variance is going to overestimate the true variance. Okay, and if you take a look at the t-test, if your standard error is overestimated, then your t statistic is going to be underestimated. Okay, it's going to be lower than the actual t statistic. Now, in that particular case, then the probability of type 2 error is going to be higher. So the probability that you fail to reject the false null hypothesis is going to be larger. So that's going to be kind of like the issue on the bias of OLS variance and the consequence of the bias on the t statistics. Now, again, in advance, it's going to be quite difficult to say whether or not the bias is positive or the bias is negative. And thus, it's going to be quite difficult for us to say whether our t statistic is overestimated or is actually underestimated. All right. I'm going to open up the floor, for you to ask questions and clarification before I actually go and discuss about testing for serial correlation. Go ahead. Okay. Good. All right. So anytime, if you have any questions, again, please let me know. I just want to make sure that everyone is in the same frequency in terms of understanding the core principles. And then, once you go back and then study independently, you can, drill further on the empirical exercise as well as, the understanding of this lecture material. All right, so I'm going to first discuss about the testing of the AR1 serial correlation, and how can we deal with different estimation issue. Okay, all right. So in this particular section, we will test for serial correlation in the simple AR1 process. So we're going to assume again that there is this autocorrelation of degree 1 or AR1. So the null hypothesis is that there is no serial correlation. Okay, so technically, if there is no serial correlation, it means that the autocorrelation coefficient is equal to 0. Okay, so when you do any kind of testing, you always have to state your hypothesis. And you always want to start with the null hypothesis. In this particular case, the null hypothesis is rho equal to 0, which indicates there is no serial correlation. Okay. However, you know, as we already discussed in many occasions during the semester, when we have the following regression specification, we can never see the error terms. Okay, why? Because it's not observable, and we don't have the data for the true error terms in the population. So if we don't have the error terms at the population level, what can we do? Any idea? Any insights? If you don't have the error terms at the population, what can you do? Well, you can always use the sample analog. Okay, so what's the sample analog? Well, the sample analog of error terms is going to be the residual. Okay, and so you're going to use the residual as the sample analog of the error terms. Okay, now in this particular discussion, we're going to assume that there is strict exogeneity assumption. Okay, so if you recall the specification, so the strict exogeneity assumption means that there is no correlation between the shock and the residual at t-1. Okay, what would happen if there is no strict exogeneity assumption? Well, we're going to relax the assumption later on, which is relatively straightforward. But let's focus on the case where we assume that there is strict exogeneity assumption. So what do we have to do? Well, it's actually quite straightforward. The first thing that you need to do is you just have to run the OLS regression. Okay, so we can use a basically we can use a more general terms here. So in this particular case, we can use yt, you know, as a function of x1t, x2t until xkt. So once you do your regression, you're going to save the residuals. Okay, so once you have the residuals, you're going to regress. U hat t on u hat t-1, and recall that in this particular regression specification, there is no intercept. Okay, again, in this particular regression, there is no intercept. So when you do your regression in Stata, you want to ensure that you have the no constant option turned on. So we're gonna look at that in a moment. And then you're going to obtain an estimate of the autocorrelation coefficient, the rho hat, and then you're going to use the t statistics to test whether or not we reject or we do not reject the null hypothesis. Okay, so again, given the statistics on the estimated correlation coefficient rho hat, we're going to conclude whether we reject or we do not reject the null hypothesis. So that's basically kind of like an overview on the way that we should regress the lag. Okay. All right. Any question so far for this particular example? All right. Cool. Okay, so I'm going to continue. So one of the tests that we can use is actually called the Durbin-Watson test. Okay. However, I'm not gonna focus much on the Durbin-Watson test. Why? Because there are some issues related to the Durbin-Watson test, and so I'll give you I think a very quick, the issue with the Durbin-Watson test. So the issue with the Durbin-Watson test is that there is going to be some regions in the critical values of the test such that you're not going to be able to make a conclusion. Okay, so if you fall into this particular critical values, you're not going to be able to say whether you reject or you do not reject the null hypothesis. Okay, and then the Durbin-Watson test is going to assume strict exogeneity. Okay, and in practice, you may not be able to fulfill the strict exogeneity assumption, and so using the DW test is something that you don't want to rely on. So in particular, if you follow Jeffrey Wooldridge Twitter account, I think a month ago he mentioned that one of the tests that needs to be retired is the Durbin-Watson test. Okay, because of the inclusive nature of some critical values, as well as the very strict exogeneity assumption. Okay, so for now, I'm going to skip it, and I'm going to encourage you not to use the Durbin-Watson test because the assumption behind it is very much hard to fulfill. And so we're going to use a test where we can actually go without the strict exogeneity assumption. Okay. All right. Any questions so far before I continue? I'm going to hold the Stata example until after I finish the discussion on the testing for AR1 autocorrelation without the strictly exogenous regression. All right, cool. So again, in many applications, the explanatory variables are not strictly exogenous. So in this particular case, there is a correlation between the variables that we observe in the data and the lack of the error terms. Okay, so if there is a correlation between the factors that we observe as well as the lack of the residual or the error terms, then the consequences is going to be invalid t-test and then DW statistic. So if you guys can recall that the estimating equation is the following. Okay, so if there is a correlation between the residual as well as the error terms, which is due to the relationship between UT-1 and then the XT, This means that the row hat and the t statistics is going to be invalid. Okay, so if it's invalid, then our conclusion on whether or not there is a serial correlation or not is going to be invalid, or it's going to be false. Okay, so in the case that there is no strict exogeneity, how should we change the regression specification? Okay, so before we go into an example, I'm just going to provide you with a very brief example on the lag-dependent variables. And so in several applications, it's actually quite common for us to see a regression of YT and then the lag-dependent variables. Okay, so given your knowledge or given the information that you have about t-1, what's going to be the best prediction for the value of y in this particular period? So your best predictor in this particular case is beta 0 plus beta 1 YT-1. Okay, and in this particular case, we're going to assume that there is no correlation between the error terms as well as the YT-1. Well, this doesn't necessarily hold. Why? Because although it's not correlated with YT-1, YT can be correlated with YT-2. Why? Through the UT-1. Okay, so basically in this particular case, when you regress YT on the lag, the YT-1, the covariance between UT and UT-1 is never going to be 0 by design. And so there's always going to be autocorrelation. Okay, so again, if you have or you do a regression on YT and then YT-1, then one of the direct consequences is that there is going to be a serial correlation. Okay, so even without testing, by design, you're going to have a serial correlation in your model. Again, having a serial correlation is not a sin. It's a feature of the data. So the question is how you actually approach the modeling to accommodate the fact that there is a serial correlation or there is autocorrelation in the data. Okay, so that's going to be the strategy. Okay, now what is going to be the difference between the initial tests that we did and in this particular case is the Durbin's alternative statistic? It's actually not much. So basically the step 1 is still very much the same. So you regress y on x1, x2 until xk. And then after that, you're going to obtain the residuals. And after you obtain the residuals, you're going to regress the residuals on the lag of the residual. But in this particular specification, you're also going to obtain, or you're going to use the explanatory variables. Why do you want to include the explanatory variables in this particular specification? You want to include the explanatory variable just to accommodate the fact that the UT-1 or the lag of the residual could be correlated with some explanatory variables in the model. If that's the case, then controlling for the explanatory variable is going to get rid of the potential bias. Okay, and after you do that, basically you can get the t-statistic on the rho hat and then test whether or not rho is equal to 0, or you're going to test whether there is no serial correlation or not. So that's going to be kind of like the idea going forward. Okay, so again, the only difference is going to be in the step X3 regression. On the Durbin-Watson test, you're just going to use UT on UT minus 1. But in the Durbin's alternative, you're going to use U hat T on U hat T minus 1, XT, X1, X2 until XK. Okay, so again, the inclusion of X1 until XK allows the XTJ to be correlated with UT minus 1. Okay, so that's basically the idea. All right, any questions so far before I continue to Stata and have a discussion on the example of this? Go ahead. All right, very good. I'm gonna actually go back to Stata and then to show you just a glimpse of how we do the the testing for serial correlation. Okay, so for this particular purpose, I'm still going to use the same Phillips curve data. Okay. However, we're going to use the regression on the static Phillips curve, just to understand the correlation within it. So actually, I'm going to clear this first, and then I'm going to use the Phillips curve data again. Okay, and then again, with any data set, we want to declare the time series. Now I'm going to regress the inflation and unemployment. Oops, sorry, I'm still sharing the screen, so let me switch to Stata. My apology. All right, so you're going to regress inflation on unemployment before 1996. Okay, and then after you do this regression, okay, following up on step 2. So the step 2 is you want to predict the residual. Okay, and then once you predict the residual, you're going to regress the residual on the lack of the residual. However, you have to remember that there's supposed to be no constant in the regression specification. Okay, so with this in mind, we can make the regression. So if you look at the results of the regression, what do you conclude? Do you conclude that there is no serial correlation, or do you conclude that there is a serial correlation? Any thoughts? If you look at the result of the regression, what do you think? Can you conclude that there is no serial correlation, or the evidence actually tells you that there is serial correlation? Okay.
I think there is a serial correlation, sir, because the coefficient, the p-value of L1 is significant.
Okay, very good. So who answered? I cannot see it on Zoom.
Krishna, sir.
Okay. All right, thank you, Krishna. So yes, Krishna is correct. If you look at the p-value is lower than a significance level of 5% and even 1% or 0.1%. And so we can conclude that we reject the null hypothesis. And if we reject the null hypothesis, then we can conclude that there is, there is a serial correlation. Okay. Again, the p-value shows that you reject the null hypothesis, and if you reject the null hypothesis, it means that there is a serial correlation. Now, if you recall, this particular regression suggests that there is the strict exogeneity assumption. Now, you can actually relax the estimating equation. So instead of just regressing the residual on the leg of the residual, you can actually include the explanatory variable. In this particular case, you can actually now include unemployment. And if you include unemployment in the regression specification, then you can now accommodate the fact that the lag of the residual could be correlated with the unemployment variable. Okay, so this is an example when there is no strict exogeneity. Okay, and then we can run the regression. And after including the unemployment variable, we can observe that the estimated autocorrelation coefficient is still statistically significant. It means that it's different to 0. Okay, and then it means that we reject the null hypothesis. And so whether you use the strict exogeneity assumption or there is no strict exogeneity assumption, you can conclude that there is a serial correlation. Okay, so from this particular exercise, if you use a wrong specification for your estimation, then you could actually obtain not only a bias estimate on the inflation unemployment relationship, but a wrong specification could also lead you to a autocorrelation or serial correlation. So one of the reasons that we want to have a correct specification in the beginning is to allow you to avoid bias or inconsistent estimate, but it could also avoid serial correlation, although it is basically not guaranteed. Why? Because autocorrelation or serial correlation is actually a feature of the data. All right. Any questions until this point? Okay, very well. So if there is no question, I'm going to allow you to take a very short break. So please take a break until 2:15 p.m. And then please return so that we can complete our discussion. We still have 2 remaining subtopics, which is the higher order correlation as well as the remedies and then the associated example in Stata. So please be back by 2:15. Okay, so we're going to restart the discussion, and we're going to discuss higher order autocorrelation. So in the previous discussion, we assumed that the error terms follow autocorrelation of degree 1. However, it's very much possible in empirical work that we're going to have higher order autocorrelation. And so recall that in the earlier part of the lecture, we can try to identify what's the optimal leg length. Is it leg 1, leg 2, or leg 3? Given empirical data using the information criteria. And so basically, we're going to try to understand the AR2 process and the ARP process in such a way that we test the serial correlation, taking into account the correct leg length. Okay, so before we proceed into the testing, then we just want to discuss what's an AR2 process. Okay, so an AR2 process is the following. So instead of just a function of ut minus 1, it's also going to be a function of ut minus 2. So the step in testing for an AR2 process is going to be quite similar. So it's going to be step 1, which is similar, step 2, which is also similar, but now in step 3, instead of just regressing the residual on the leg of the residual, you're going to also regress on the leg 2 of the residual. Now the step 4 is also going to be quite different. So instead of just using the t-test, to test whether or not there is a serial correlation on the autocorrelation coefficient rho hat 1, we're going to test whether or not simultaneously rho 1 hat and rho hat 2 is equal to 0. Okay, and so we're going to use the f-test. Okay, so that's going to be the AR2 process. Now, it's also possible that in the data, not only that you're going to look at AR2 process, but it could also be the case that it's an ARP process. So it could be AR to the degree of 3, or for example, AR to the degree of 4. It could be an AR5 process. So whether it's an AR1 process or it's an AR4 process, it's going to be, determined empirically. So how do we determine empirically the leg length? We're going to show you in Stata after this. But again, in general, we can never know what's the structure of the AR in the beginning. So that's something that we need to look at empirically. So again, the difference is now, instead of just regressing the residual on the leg of the residual, but we also regress it on the leg 2 of the residual, leg 3 of the residual, until leg P of the residual, where P could be 4, P could be 5, P could be 6, depending on the degree of the process. And remember that we also include the explanatory variables and that there is no constant involved in the regression. Now, once you do the regression, what you want to do is you want to test that rho 1 hat, rho 2 hat, until rho p hat are all simultaneously equal to 0. So in this particular case, we can suggest that we can conclude that there is no serial correlation. However, if we reject the null hypothesis that rho 1 hat, rho 2 hat, and so on until rho p hat is equal to 0, then there is an evidence of serial correlation in the data. And so that's going to be the general case of autocorrelation. Again, we can never limit ourselves into an AR1 process. In practice or empirically, we can find data that could be AR2, we can find data that could be AR3, or we can even find data that is AR4. Okay, so again, this is just the general step, and we're going to go through it, in the next example in Stata. Okay. Now, what about the testing itself? Yes, we've discussed that we can use the f-test. However, there is an alternative to f-test. So the alternative to f-test is going to be the Lagrange multiplier statistic. So you can use f-test, you can use the Lagrange multiplier statistic. Okay, so these statistics are going to be provided by the, it's going to be all provided by the Stata, so you don't have to calculate it manually. However, you need to be able to understand how to actually interpret the results of the data. Okay, so start with the hypothesis. So you can start with the null hypothesis, and then given the results of the test, you can always use the p-value. Okay, so given the results of the test, particularly the p-value, what can you conclude? So that's going to be the idea moving forward. Okay. All right. So in this particular test, it's called the Breusch-Godfrey test. So the difference between the Breusch-Godfrey test and the Durbin's alternative test is that the Breusch-Godfrey test do not include explanatory variables. Okay. However, in the previous test, you can see that we also include the explanatory variable. So in this case, we use the Durbin's alternative. So what's the difference in the assumption between the Durbin's alternative and the Breusch-Godfrey test? So basically, the Breusch-Godfrey test still assumes that there is a strict exogeneity. However, in the Durbin's alternative, we assume that there is no strict exogeneity. So that's going to be the difference between the Breusch-Godfrey test and then the Durbin's alternative test. The question is, which one should we use? The answer is, again, it's going to depend on the empirical evidence. All right. Any question on the AR2 process as well as the ARP process before I return to Stata? Go ahead. Awesome. All right. So I'm going to return to Stata, and for this particular exercise, we're going to use a different data set. Okay. Okay. So for this particular exercise, I'm going to use the internet depth data. Okay. So what does this particular data set tells you? So this particular data set tells you about the variable I3. So variable I3 is the 3-month T-bill rate. And then you also have INF, which is the CPI-based inflation rate. So there is a CPI-based inflation rate. There is a producer price index or PPI-based inflation rate. There is also the WPI or the wholesale price index inflation rate. The most commonly used inflation rate is the one that is based on the consumer price index. We're also interested in the DEF. So DEF is basically the federal budget deficit as a percentage of the GDP. Okay, so what are we interested in? So what we're interested in is to look at the relationship between the inflation and the 3-month T-bill rate, and the relationship between the budget deficit as a percentage of GDP on the 3-month T-bill rate. Okay, so we're going to do a static regression using the level variable that we have. So basically, we're going to regress I3 on inflation and then budget deficit as a percentage of GDP. Okay. Oh, so before that, I also need to set the time series. Now, given the regression residuals, then what I'm going to do is I'm going to predict the residual. Okay. Now, before we do any further analysis on the residual, it's always nice to actually look at the correlogram of the residual. Okay, and then if you can see the correlogram of the residual, you can see that there is a significant autocorrelation on leg 1. There is a significant autocorrelation on leg 2, and then there is a significant autocorrelation on leg 3. Okay, so given this correlogram analysis, we can say that, oh, maybe we can include like 1, like 2, like 3, and like 4. However, if we want to be more certain about the number of lags that we can include in the regression, then we can use the Stata's FARSOC package. Okay, so basically you want to understand what's the optimal length that we can get from this data set. So basically I'm going to use the FARSOC for the residual U. And so for this particular analysis, you want to have it until lag 8. Now, recall that what we want is to find the lag length with, using the Akaike information criterion, the Hanan-Quinn information criterion, or the Schwarz-Bayesian information criterion. Now, if you look at this criteria, then you see that they are in agreement. Okay, whether you use the AIC, the HQIC, as well as the SPIC, you can observe that lag length of 2 is the optimal lag length. Okay, so that's going to be basically the idea. Okay, so given our knowledge that the lag length is 2, then we can do the regression to understand whether or not there is a significant relationship, and then there is an autocorrelation. So basically you're going to regress the residual on the lag 1 of the residual, and then the lag 2 of the residual, and then the explanatory variables of interest. In this particular case is inflation, and then budget deficit as a percentage of GDP. Okay, this is basically step 3 in the slide deck that we just discussed. Okay, now again, if you look at it individually, so the lag 1 is statistically significant, and then the lag 2 is not statistically significant. So we're not going to stop here. Again, why we actually want to use the F-test. So basically, we want to test whether the lag 1 U is equal to the lag 2 of U and equal to 0. So basically, we want to do an F-test. Okay. Now, after we look at the results of the F-test, what can you conclude? Do you reject the null hypothesis, or do you not reject the null hypothesis? Any thoughts? What does the p-value of the test suggest to you? Does it reject the null hypothesis, or it doesn't reject the null hypothesis? Using the p-value. Okay, so basically, if you look at the p-value, so the p-value is below the significance level of 5%, it's even below the significance level of 1%. It means that you reject the null hypothesis, and if you reject the null hypothesis, it means that there is a serial correlation up to order 2. Okay, so another way of looking at this more not efficiently. I just want to show you the nooks and crannies of the test, but if you want to do it in a straightforward manner, you just have to regress I3, and then inflation, and then the budget deficit as a percentage of GDP. Okay, and then you run the regression, and after you run the regression, you're going to do E-stat, and then Durbin alternative. And then you're going to specify that we're going to use lag 1 and lag 2. Why do you want to use lag 1 and lag 2? Again, the analysis that we did so far right here indicates that the optimal lag length is 2. Okay, so that is why we use lag of 1 to 2. Now, the Durbin's alternative test shows you that, again, the p-value suggests that we reject the null hypothesis. And if we reject the null hypothesis, we can conclude that there is autocorrelation of degree 2. Okay, so that's going to be the results of the regression. Any questions, clarification before I go and continue on the remedy for the regression? All right, let me continue back with the lecture note. Okay, so basically we're going to go back to the scenario of AR1 serial correlation. So you have a model, and after analysis of the residual, you find that there is an AR1 serial correlation. Now, given that there is an AR1 serial correlation, what can you do to transform the model to basically eliminate the serial correlation? Well, actually, you don't necessarily eliminate the serial correlation. So I guess a better terms would be we can transform the model to accommodate the serial correlation, because the serial correlation is always going to be there, but we just want to accommodate it. We want to have a model that accommodates it. So one way that we can basically do is first to take the lag equation. Okay, so we have a basic model of yt, para0, para1, xt, and then ut, and then we take the lag equation. Okay, and then based on the lag equation, we're going to multiply it by rho. So you multiply this by rho, and consequently on the right hand side, you also need to multiply it by rho. So rho is going to be the estimated autocorrelation coefficient, which is which is the characteristics of the data. Okay. Now the next step is to subtract the original equation with the lag equation. Okay, so you have the yt para0 plus para1 xt plus ut, and then you have rho yt minus 1 para0 plus para1 rho xt minus 1 plus rho ut minus 1. Okay, and then once you subtract that, this is what you get. You basically have yt minus rho yt minus 1, and then if you sorry, there's a rho here, and then you have 1 minus rho para0, and then you have para1 xt minus rho xt minus 1, and then you have ut minus rho ut minus 1. Suppose that yt minus rho yt minus 1 could be written as yt tilde. Okay, so you have yt tilde 1 minus rho para0 plus para1 x tilde t. Okay, now for the first observation, recall that in the first observation you don't have yt minus 1, and so in that particular case you can just use the observation at period 1. Now this transformation of the OLS to obtain a more efficient estimate is called a generalized least square. Okay, So if you recall in the heteroscedasticity example, we discussed about weighted least square. So weighted least square is a very specific case of generalized least square. So given an issue with the model, be it heteroscedasticity or in this particular case, autocorrelation of degree 1, then we want to make a transformation in such a way that the result of the GLS is blue. In the case we get an unbiased or consistent result, and it also produces the lowest variance. Okay. So this is the GLS estimator. Basically for period 2, 3 until n, we want to regress YT tilde. Recall that YT tilde is YT minus rho YT minus 1, and then you have the X1 tilde, X2 tilde until XK tilde. So that's the transformation that you need to use. Again, in the first period, okay, Y1, you basically do not have Y0. So in the first period, what you need to do is just 1 minus rho square to the power of 1/2, and then Y1. And similarly, for X tilde, you're going to have 1 minus rho square to the power of 1/2, and then XK. Note that you're not going to calculate it manually. However, I just want to make sure that you understand the reasoning behind why we want to transform it using the Y minus rho. Okay, this method is also called the quasi-differencing method, okay, to accommodate for the AR1 serial correlation. Okay, any question before we go and discuss the estimation process itself? Okay, for those of you who have a sort of connection problem, that is okay. I'm gonna upload the recordings of this lecture, so you have a reference for when you do your independent study. Okay, so I'm going to continue. Again, if we look at the previous estimation, you don't know what's the value of rho. That's something that we see in the population level. We don't see in the population level. So if we don't have rho, how can we do the quasi-differencing? Any idea? What's the alternative if we don't have rho at the population? Well, if we don't have rho in the population, again, you can always use the sample analog, okay, which is the rho hat. So where do you get the rho hat? Well, you get the rho hat from the regression of the residual and the lag of the residual, okay? So from this regression, you'll get the rho hat, and then you can use the rho hat in this particular example. So the generalized least square that uses a sample information is going to be called feasible GLS estimator. Okay, so again, a GLS estimator that take advantage of the information on the data is going to be called the FGLS. Okay, so let's go one by one on the step. Again, there is a built-in Stata function that allows you to do the regression. However, for you to really understand kind of like the underlying concept of the model, it's always nice to see the procedure before we actually use the model. So going back to the step 1 that we saw in the previous slides, we're going to regress YT on the explanatory variables of interest. In this case, it's X1 until XK. And then once you do the regression, you're going to obtain the residual. And once you obtain the residual, you're going to regress the residual on the lack of the residual. And then you're going to obtain the rho hat. And then you're going to use the OLS to regress, using the rho hat. So basically, this is going to be the estimating equation using rho hat that we estimate from the data. So what's going to be the property of the FGLS estimator? So the FGLS estimator is going to be asymptotically more efficient. So why is the FGLS estimator more efficient than OLS? Because the OLS ignore the AR1 serial correlation. However, the FGLS estimator take into account that there is an AR1 serial correlation. So by taking into account the fact that there is an AR1 serial correlation, the FGLS estimator is asymptotically more efficient. And there are two different FGLS estimation methods. We have the Cochrane ORCID or CO estimation. So in the Cochrane ORCID estimation, you're going to omit the first period observation. Why do you omit the first period observation? You omit the first period observation because there is no YT-1. So the Cochrane and ORCID estimation basically gets rid of the first observation. On the other hand, we have the Prais-Winston estimation. So the main difference with the Cochrane ORCID is that they still take advantage of the first period observation. So basically, if you take advantage of the first period observation, you have more information. So if you have more information of the data, that it could probably lower your standard error or your variance. So again, there is not much of a difference other than one includes the first period observation, the other one excludes the first period observation. But again, it's always back to the empirical example. So I'm going to show you that in Stata right now. Now, for this particular exercise, we're going to use a different data. So for this particular example, we're going to use the barium data. So let me find the barium data in the data set. Okay, and then so we have the barium data. So this is data from the study by Krupp and Pollard in 1996. So basically, the study analyzed the effects of anti-dumping filings by the US chemical industries on imports of various chemicals. So here we focus on basically one industrial chemical, which is the barium chloride. That's why we call the data set the barium, which is a cleaning agent used in various chemical processes and in gasoline production. So in the early 1980s, US barium chloride producers believed that China was offering its US imports an unfairly low price. Okay, so by importing an unfairly low price, we are committing to what's called dumping. And the barium chloride industry filed a complaint with the US International Trade Commission in October 1983. So if you have an import of goods which is relatively cheaper, then the local industry basically cannot compete, okay, with a cheaper price. Again, as a producer, if you have a cheaper product with basically no difference in quality, then you want to go for the cheaper one. And so that's why the barium chloride industry filed a complaint on the US International Trade Commission, and then the International Trade Commission favored the US barium chloride industry in 1984. Okay, and so basically, what is going to be the effect of the filing on the import of basically the barium chloride from China. So that's going to be the exercise that we want to do. All right, so after we have the data, I'm going to declare that it's a time series, which start in the second month, which is on February of 1978. Okay, and then I'm going to indicate the time dummies. So I'm going to generate a variable M. Variable M is just the month indicator of the date time. Okay, so the first regression that I'm going to do is I'm going to regress the log of China import. So I'm actually gonna I'm gonna do this. I'm gonna regress the log of China import on the log of chemical import, L gas, and then this is the exchange rate, and then this is 6 months before the filing. This is 6 months after the filing to the ITC, and then the December. And you can also include what's called the month dummies. Why do you want to include the month dummies? You want to include the month dummies to ensure that you take into account any seasonality in the outcome of interest. Okay, and the seasonality here is on the monthly level. So this is a regression where we take into account the seasonal dummies. Okay, so that's the regression. Again, what we're interested in is this variables. Now, again, one of the problem with this particular thing is going to be the residual. So there could be a serial correlation. So we can predict the residual, okay, and then given the residual, we can analyze what's the lag. Okay, so since this is a monthly data, then perhaps using the Hanan Queen or the Swartz Bayesian information criteria is going to be more preferable. So we have here an AR1 process. So since this is an AR1 process, you can do this, the same regression that you did, and then use the ESTAT Durbin alternative for lack of one. Okay, and then just by looking at the p-value, you can conclude that you reject the null hypothesis. And if you reject the null hypothesis, then there is an evidence of AR1 serial correlation. Now, if you have an AR1 serial correlation, then one of the solutions that you can do is to use the Prais-Winston estimate or the Cochrane-Orchid estimate. Basically, there's not much difference in the two estimates other than the Cochrane-Orchid estimate do not take into account the first period observation. Okay, so basically, instead of just using the regression, we're going to use the Prais-Winston, and then we can add the robust standard error here just to take into account any form of heteroscedasticity in the data. Okay, so you're gonna run the regression. Okay, so after you run the regression, then here you can identify the results of the regression. So basically, the results of the regression shows you that basically there is no effect of the filing on the imports decision. Okay, so even though there is a filing against the import, there is no effect of that filing. Okay, and we can also use the same regression, but instead of using the Prais-Winston, you can use the Cochrane-Orchid estimate, where in this particular estimate, we do not take into account the first period observation. Okay, and then we run the regression, and basically by looking at the estimated coefficients on the timing of the filing, we don't see any effect of the filing on the chemical imports from China. So what does I tell you? So after we take into account the potential serial correlation, we can conclude that there is no effect of the International Trade Commission filing on chemical imports from China. And so this is an example of an exercise in which there is an AR1 serial correlation. And given the AR1 serial correlation, you make a transformation such that you take into account the AR1 serial correlation. And the transformation that you use in this particular case is quasi-differencing. Okay. All right. Any questions on the method to estimate the model using Cochrane ORCID or the Prais-Winston, which is an FGLS regression? Go ahead. All right.
Sir?
Yes, go ahead.
Question, and it's kind of related with panel data. So I've been seeing that the way we deal with heteroscedasticity is that the goal is to treat for serial correlation. And my question is that I think in panel data, if I recall, we only use robust clustered standard errors. So my question, is there any instances where we want to treat for serial correlation in panel data, or perhaps can we use FGLS in panel data? Thank you, sir.
Yes, so basically in panel data, you can take into account serial correlation within a particular cluster by using the cluster robust standard error. Okay, so suppose that you have many clusters. It could be an individual cluster. It could be household level cluster. It could be a district level cluster. So whatever cluster it is, we can expect that there could be some unobserved correlation on the unobservable. Now, in that particular case, then we need to control for it using the cluster robust standard error. So that is totally fine. Okay. Is there any case where we use FGLS in panel data? The answer is yes, but that's going to be a more complicated model. There is one that you will see in advanced panel data if you take microeconometrics. Okay, any other questions, clarifications about the method that we just discussed? All right, awesome. I think we can stop here. And next Monday is going to be our last lecture. So in our last lecture, we're going to discuss about limited dependent variable. So we're going to do a regression where the dependent variable is a binary variable. So for example, whether or not you have a insurance or you don't have an insurance, okay? And if we have time, we're also going to discuss about the multinomial model. So a multinomial model is where the dependent variable is a categorical variable, but it has more than 2 values. So that's going to be the agenda for next week. I'm going to close the discussion today, and I'll see you guys next week. Stay safe and stay healthy. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.